Thanks, Korika. Good morning, everyone. I hope the slides are visible on the screen. Yep. So, whenever a project is going live or we have to push it from a lower environment to higher environment, many times we realize or we get these challenges. The availability of the application seems to be going low with each new test that we are doing in terms of the availability. The latency of the application increases as we see rise in production users. To mitigate, the most common approach or the simplistic approach that we all use is to throw infrastructure at it. So we keep the infrastructure to its max because we are worried that it should not fail on the go live date, and that increases our cost, and at least for the short duration, it kind of hits our operating margin. At the same time, when any error happens, in many cases, we observe that transactions are getting lost and we have blind spots in our observability solutions, and we are not able to trace them and solve the problem. Finally, once we know that we are through the storm of the go live, when my production cycle becomes normal, what is the best fit infrastructure? There is no empirical way of determining that, or there is no way that we can judge it in a cost effective manner. We all might have come across either of these problems or all of these problems at some point during a go live for our project. Just take another example where Delta Airlines 2,300 flights got to be cancelled because of a malfunction in their equipment. FedEx had 300 million losses because of a security issue. Amazon storage services faced a 4-hour downtime because of improperly validated run book. Similarly, Equifax was hit by DDoS attack where 147 million users were impacted, amounting to huge losses. So these are all real life examples that help us reiterate the fact that production outages and interruptions are costly and we need to act on it before we go to production. That brings me to the current topic that we are presenting in this session: chaos engineering for creating and enabling secure, resilient, and scalable digital transformations. I am Karteek Gadiraju. I am a site reliability engineering architect at Microsoft Global Services Center, India. In my 18 years, I have been a quality architect, taking care of tools or test automation and performance uh, as part of my day job. And as part of this session, we'd like to share some of the best practices that we used so that you can take it back to your projects. And during Q&A, if you are able to learn some of the best practices from your side, that would be an added advantage and a good knowledge share for all of us. In this presentation, we would like to see how post COVID, most of the digital transformations are happening and people are preferring to move to cloud. Complex systems are being designed not only to a simple cloud, but we have seen examples of certain customers going to multi cloud or even hybrid scenarios. The recent large scale sporting event that is happening around the world uses the digital twin, which consists of on-premise infrastructure on multiple clouds. So that adds to the complexity. Though we have shift right reliability and resiliency, they have not been able to address all the problems, and they come with their own downslides. We have to design our applications to handle failures. Resiliency is not only about reacting to a situation, it is our ability to perform, operate, and adapt to such event, and also ensure that we plan to mitigate such events in future. That brings to the reason why we need chaos testing. Chaos testing consists of four main stages. We create an hypothesis, we experiment, we analyze, and we improve. Ultimately, we measure everything and we design auto healing systems so that we can recover faster. During the course of this presentation, I would take you through a case study for a large scale messaging platform where, through proper implementation of chaos testing and the learnings from it, we were able to save of a magnitude 57% from the cost that they incurred at the time of go live. So, going to the proposed solution, my proposed solution does not include one step. There are three steps to it. First, we have to define a problem, we have to develop and execute, and finally, we have to be in the sustenance of it. Even define is not only a static definition, define itself consists of certain actions that give us valid inputs that is required to develop and operate. The first one is defining a reliability goals. Before we solve any problem, we need to understand what are we trying to achieve and what is termed as success to us. For this platform, that is a communication platform as service, which is person to messaging platform, we wanted to achieve a latency goal of 1.5 seconds for 99.95 percentage of users. The availability target of 99.9%, a throughput goal of 1 billion messages per day, with peak going up to 60,000 messages per second at any point in a day. Recovery time in case of any disaster or any failure, 15 minutes, and recovery point objective as no message loss. Though the recovery point objective is very ambitious, that was a requirement from customer, and we have to kind of work on it and try to provide a solution around it. Second, once we have defined our reliability targets or defined the goals, let's move on to the next action that we had taken, is defining the failure modes at each unit, and through performing a failure mode analysis during unit performance. What we do is, for our entire application architecture, we identify certain components and its dependencies that can cause disruptions to service. We rate each of these components based on the likelihood of their failure, whether they are common, extremely rare, and what is the impact of that failure in terms of availability, latency, monetary, or business disruption. And then we define a approach how we can mitigate or how we can solve it uh, instantaneously, or whether the recovery requires certain time, and whether the recovery approach falls under the recovery time objective for us. Once we have defined the failure modes for each component, now we go back and do the architectural static performance, where we want to analyze what communication points within my application architecture can become a bottleneck and impact the latency goals, where I want to do auto scaling in terms of enabling HPA, or vertical scaling needs to be done, so that we can come up with the best and worst case times and then build a solution around it. This is all we are doing still in the definition stage of it. From these two activities, what we learned is we did not have the proper instrumentation to measure the items at a unit level. So we went back, added the instrumentations. These are the terms which are generally used in SRE, site reliability engineering, the SLI, uh, the indicators, service level indicators, service level objectives. We added service level indicators for latency, throughput for each of the user journey that we had in our applications. By catching the defects early, we were able to solve some of the issues that happen at a unit level, rather than a top down approach where we find the problem in the deployed application and then we kind of drill down from top to find which layer actually has the error. Once we have solved the problems at unit, now the next problem statement that we have is what is a scale unit that we need to begin with. This gives us an idea whether we want to do horizontal scaling, vertical scaling, and what is the bare minimum cores, memory, or RAM to begin with. The traditional capacity planning model that we usually approach is we collect the demand forecast, we have the allocation plans, we review and sign off on it, we implement, deploy, and monitor. And this is a continuous cycle that happens. And each time there is a change in demand or forecast, we have to kind of change our capacity planning. This is a never ending cycle, and usually we get to know that our capacity planning is bad when it breaks, which is a costly time. So, as a solution for it, what we did, we tried to take a single pod as the solution was deployed in Kubernetes and see what is the max capacity a pod can handle without impacting our availability targets. So if I can get an RPS of 100 or 200 with a single pod, it does not mean I am not seeing any failures. It means that I'm able to achieve triple nine availability, and all my response times are within 1.5 seconds for 99.95 percentage of users or transactions. That's when I say one pod has this maximum threshold it can handle, and then we take around 60% of it to initiate our HPA. So that was a scale unit determination. No, that helped us to move away from normal capacity planning, traditional capacity planning, to what we call intent based capacity planning. To give more examples of a difference between how normal capacity planning works against intent based, there are three examples where I can say I want 50 cores in a cluster for the service. I am defining number of cores. It is a traditional way of doing it. I want 50 cores footprint in three clusters in multiple geographic regions. This is again a static way of doing it. I want to meet the service demand in each geo with n plus 2 redundancy. I'm again defining it in a traditional manner. But when I say I want to run my service at three nines of availability, now whatever is required to help my service run at three nines of availability, I need to encourage and have that capacity ready, even if it required to make it available during the runtime. Now, after the three steps that we have done, now we have the fourth step. After determining all my capacity plans, my workload model in terms of what the system load would look like in production, 3 months after production, 6 months after production, or 2 years down the line, I want to test it, how it will react when it fails. From intent driven capacity planning now to intent driven performance testing, which was done in conjunction with the chaos experiments. Chaos experiments, which we have defined in our unit performance in terms of which components are prone to failure. I create a hypothesis around those experiments. Say, for example, a VM can get rebooted. VM can have a process that gets killed. Those are the different type of experiments I have. For each component that is prone to failure, we will come back and create a hypothesis and conduct chaos testing along with a synthetic load. So when I say chaos testing, it's never in isolation. Define hypothesis. Say, for example, VM, I took an example. We can have a CPU pressure, physical memory pressure. These are all various experiments that we identified for virtual machine. Then we ran a traditional performance test. While my traditional performance test was running, we triggered a chaos test in a staging environment. Usually, chaos experiments are mentioned to be done in prod environment, but we should not do it if there are active users and we don't have a proper mechanism to bring the environment up if it goes down. So we did not have that confidence of doing it in prod. We ended up doing it in staging to determine the results of our experiments. We can do as ad hoc feature validation. We can make it as part of continuous delivery. We can do it as part of BCDR, business continuity and disaster recovery experiments, or we can do it during production in a game day scenario where before releasing my system to the end users, I have the deployment done in production and I want to validate using some synthetic traffic whether my production environment is able to manage the load. So, this is a snapshot of what was happening before a chaos experiment run. This dashboard is what my performance testing shows. Uh, all the services are up, meeting all the SLAs that we have set in terms of throughput, latency, and availability. As soon as I trigger a chaos experiment, I suddenly see my overall availability fell to 66.67%, but that was for that moment. It averages out if it runs for longer period, but we can clearly see what happens when a chaos experiment was triggered. All my requests started failing, and within 30 seconds, once the chaos experiment was complete, it came back up. So these are the type of metrics that we get that help us decide how resilient the system is and how to build a recovery plan for it. Some of the actions or observations we had and the actions that we took, spikes in traffic were there. All the services were request response services, synchronous. We realized to maintain higher availability and to kind of meet the recovery point objective as no message is lost, we had to shift from a request response to a queue based leveling pattern. Once we went to queue based leveling patterns, we started observing service bus client issues. This was during the unit performance. We changed to the SDK where we started getting auto retries enabled. With a spike test with 60,000 requests per second, we observed quota exceeded exceptions in our queues. So we had to go back and implement circuit breaker pattern to avoid continued retries, to give some breathing space for the subscriber so that it can process the live messages and slowly we can inject the retries into it instead of causing a bottleneck of new messages as well as retries. Transient failures for all components at unit level. We implemented the retry logic, be it a SQL connection or database connection or service bus connection. Retries were implemented so that we don't get a failure. That slightly compromises on the latency targets, but at least it improves the chance that the message will get through and the end user will get a whatever notification the end user is supposed to receive. Through all this, what we realized at the end of it is service bus was not still meeting the recovery time objective. So we went from to all active replication pattern and active configurations to cope up with outages and disasters. So now we have two service buses, both active on active replication. So as soon as one service bus stops responding, the retry would go to the second service bus and still serve the customer. Through all this, we have learnings in terms of we have to identify and address every single points of failure early. We have to install guardrails for graceful mitigation, like we implemented active to mitigate or circuit breaker. That's a graceful way of solving the problem instead of showing service unavailable or messages getting lost. Through circuit breaker, we were able to minimize the blast radius by taking out a service that was causing problem, or by taking out the retry mechanism and sequencing it more logically. We were able to reduce the impact on the new messages coming in, and through auto healing we have immunity built. When we move our workloads from on premise to cloud as part of our digital transformation, we have to understand the cloud platforms are transient in nature. Some of the issues that we get on those platforms are rare and predictable, and in some cases disruptive. Just by doing performance testing or capacity planning in a traditional manner, we won't be able to gauge or meet up the requirements that can happen on cloud. So we have to do chaos testing and engineering along with it, where our performance test or simulate or mimic a traditional user acting on the system. Through this implementation, we have certain advantages or certain outcomes that we were able to meet. We were able to meet 1.5 seconds for 99 percentage of users only. Our target was 99.95, but we were able to meet it for 99%. Though we did not meet, but we have plans in place and we are working towards meeting that target as well. With queue based leveling, we were able to achieve a 999 availability or 99.9% availability in a non DR scenario. When DR happens, it has to set up a new environment. So we are trying to optimize the timings in a DR setup. As long as it is a non DR failure, we still are able to attain three nines of availability. With queue based leveling, we were able to achieve a peak throughput of 60,000 messages per second without any failures or without any message loss. As we saw for service bus, the entire time that it took for the service to come back up was 30 seconds. So we were also able to meet the recovery point objective. And as the graphic shows, when we started off in the production, the entire cost of infrastructure was very high. Through scale unit determination and these optimizations we have done, we were able to reduce the infra cost by 57%. At the same time, the active users on the system kept growing. Traditionally, with active users growth, the infrastructure keeps on growing. But in this case, we were able to bring the cost and the size of infrastructure down. It means we were able to optimally use the available infrastructure with us. When chaos testing need to be done, while deploying a new code, when we observe changes to the usage patterns, we have to come back and change the workload model or the chaos experiments. And whenever we are trying to mitigate a problem, when we encounter a new problem in the production, when we do 5 whys or root cause analysis, see how it can be included in the chaos experiments, add it to your experiment so that in future it does not happen, or at least you are factored in a recovery mechanism for it. In the end, what we can say is normal ways of performance testing or scale units or even forecasting is not helpful when we talk about multi cloud or hybrid scenarios. We need to think about more in terms of reliability design or release engineering at the time of product design itself, and chaos testing cannot be left out of it. So we need to embrace the inherent chaos and transient nature of the cloud platforms while we attempt to build a secure, resilient, and scalable systems. That concludes the presentation. I see one question: how self healing is going to help if there are changes in dynamic XPaths from one release to another? So, this is not an automation related topic, right? Dynamic XPaths come in for automation. This is for the environment, how we do site reliability engineering or how chaos engineering helps to keep my environment up and running. This is not related to uh, anything automation related. Any further questions?